All right, so today we're going to be talking about the dot product. The dot product, filled with so much potential, so underrated, such an incredible, powerful mathematical tool. So it's going to be actually really cool to talk about the dot product. You're going to see that it has a lot of uses. Its uses actually spread from physics to computer science to data science to statistics to all over the place. Anytime you've got things that have lots of variables, the dot product ends up coming in really handy. So we're going to be talking a lot about the dot product. All right, this is going to be our basic lesson for the dot product. We're going to kind of get into like how do you find the dot product. We're going to talk about how do you use the dot product in order to find the angle between two vectors when we're looking at vectors in 3 or more dimensions, because that's kind of like a weird or different thing. We're also going to be talking about how do we do things like how do we break up vectors into component parts, like their lengths, widths, and heights, okay, along particular lines. And it'll be really interesting. We'll get these things called projections, and these projections end up becoming really important and very valuable. So, looking forward to talking with you about the dot product. So, let's talk about calculating the dot product and how we calculate the dot product. First, I want to get some notation again. So, we've got u here. U is our vector, okay? And I'm going to represent u in component form, and it's going to be u1, u2, u3. What you'll notice about u1, u2, u3, one, it's a vector in 3 dimensions, right? It's got an x, a y, and a z component. Also notice that we use u for each one of those components, and then we utilize a subscript. You're going to see this, and I'm actually pretty much going to stick with that a lot more now that we're getting more sophisticated in terms of our math, okay? So if I say, for example, I have a vector v, v will look like this. It'll be v1, v1, no line over the top of it, v2, v3. Okay, so your vector has got this little thing over the top of it, or it'll be bolded, and then your components, they'll have subscripts. Okay, they'll have subscripts, and that represents the individual components. Okay, the reason why this is important is because what we're going to do is we're going to talk about what happens when you dot, okay, or take the dot product of two vectors. So if I take the dot product of u dotted with v, okay, and that's how we write it, u dot v, it's going to equal u1 v1 plus u2 v2 plus u3 v3. So what we'll do is we'll multiply each component by their position. Okay, notice the first position components get multiplied together. The second component get multiplied together. The third components get multiplied together, and then we add up those multiplications. Same thing qualifies for when we're doing it in 2 dimensions. Okay, so like if I have u as a 2-dimensional vector, u1, u2, and v equal to v1, v2, then u dotted with v in 2 dimensions is going to equal u1, v1 plus u2, v2. And that's actually how we end up defining the dot product. Okay? Really important that if you have 2 vectors and they're not actually inside of the same space, you can't dot them. You can't take their dot product. The calculation should show you that that's the case, but just something really important to remember. You can only work with vectors that are inside of the same space. Okay? Otherwise, you get all sorts of problems until you get into linear algebra, and even then, there are still restrictions on the kind of stuff that we can do with vectors. But remember, just, when you're doing algebra, when you're doing scalar multiplication, or you're doing anything with like these dot products or cross products, when we see cross products, that the 2 vectors have to be inside of the same space, right? Either in 3D or in 2D in our case, or, we'll talk about these more R2, R3, R4, etc. Okay? So that sets up our calculation. So let's do an example. So here's an example. Let's say, for example, I want to find u dot v. Okay, so we want to find u dot v, and we're going to set up that u equals 1, 2, 3, and v equals -1, -3, -1. So u dot v, what we're going to do is we are going to multiply component-wise. So 1 times -1 plus 2 times -3 plus 3 times -1. So that gives me -1 plus negative 6 plus negative 3, and that ends up equaling negative 10. And there we go. That's the basic dot product. We're going to see this tons of times, so pay attention as we're going along. You might need to stop, kind of do a couple problems with this just to kind of get it ingrained. But once you do, you're all good to go. Okay? Let's take a look at another example. We'll take example number 2. And this one we'll actually do in standard unit form. So let's take 3i plus 6j minus 2k. And we're going to dot that with 4i minus 3j. So we'll dot those two vectors together. What I want you to notice is right, there's no k inside of our second vector. Okay? All right? And what we need to do is we need to be sure, okay, like make sure this is in 3D space. So let's just say, yes, it is in fact in 3D space, and so we can in fact do the dot product, right? We're not going to get tricky here. So what we're really going to do is we're going to say, okay, this is 3i plus 6j minus 2k, and we'll dot it then with 4i minus 3j plus 0k. Remember that when we went in and we added them together, or we took the dot product, we actually did it component-wise. And when we look at standard unit form, our components are the values in front of I, j, and k. So this dot product is going to be 3 times 4 plus 6 times negative 3 plus negative 2 times 0. So that's 12 plus negative 18 plus 0, which ends up equaling negative 6. And so our dot product is negative 6. A couple other things to kind of remember here. Unlike scalar multiplication or addition, the result of a dot product is actually another scalar. Okay, it's another scalar, it's an important scalar, but what that means is that it's just a single number. Doesn't matter how many or how big the space is in, if you're in like 4-dimensional space, 10-dimensional space, whatever it is, when you take the dot product of two vectors in that space, what you're going to get back is you're always going to get back a scalar. You're going to get a single value like negative 6 in the case of this answer, or negative 10. So that's how we actually go out and find the dot. Okay, so when we were doing algebra, the algebra on vectors, I really didn't feel too much of the need to actually talk about the properties of algebra for vectors. And a lot of that's because a lot of it kind of is pretty intuitive, not too difficult. It kind of looks a lot like what we would be doing when we work with like kind of the real numbers or polynomials and the like. The dot product's a little bit different. So what we want to do is we want to actually kind of enumerate what are the characteristics or the qualities of the dot product, because it's kind of so new. So let's suppose that we have u, v, and w are vectors, and c is a scalar. Okay? And notice that my u, v, and w here, they're bolded, and that actually indicates to you that they are in fact vectors, if I am doing this utilizing typeset. First things first is the dot product is commutative. What that means is that u dot v is going to equal v dot u. And we're going to prove this, and we're going to do a lot more proving inside of this particular chapter, because it's going to be kind of helpful, and it's going to get you used to kind of doing some advanced mathematics. So we're going to have u, okay, let's say, for example, that it's in 3D, okay? So we've got u1, u2, u3, v1, v2, v3. So we'll let u equal, u1, u2, u3, and v equal v1, v2, and v3. So u dot v, by definition, is going to end up equaling u1, v1, plus u2, v2, plus u3, v3. Okay? Got that direction, u dot v, right? Multiply component-wise and then add them together. Now, scalars are just simply real numbers, and real numbers can be multiplied and added in any order. They are, in fact, commutative. We can actually accept that without any kind of proof. So what I can do is I can switch around v1 and u1, v2 and u2, and v3 and u3. So this gives me v1 u1 plus v2 u2 plus v3 u3. Okay? And that's because, like 2 times 3 is the same as 3 times 2. And that's all these values inside of it, all these components are. They're just real numbers. So this is then going to equal v dot u. And that actually finishes it out. Okay? We just showed that u dot v equals v dot u, and our proof is finished. That's what this little thing, by the way, means. That means I'm done with proof. Secondly, we can distribute the dot product. Not distributed, but distribute the dot product. And so what this means is that if I have u, the vector u dotted with, and we've got v plus w. Okay? So we've got a vector, we're going to dot with two vectors that have been added together. That will equal u dotted with v plus u dotted with w. Okay? And it seems obvious. You might think to yourself, okay, that's totally obvious, but it's not really. Okay? Because like sometimes when you do different kinds of calculations, you get different kind of results. Let's just prove this. Okay? We're going to have, we're going to presume that u and v and w. We'll let w now equal, and we'll have it be w1, w2, and w3. So we'll add that in. We'll add our next vector. And so u dot v plus w, okay, is going to equal, it'll be u dotted with, and we're going to add v plus w together. So that's going to be v1 plus w1, comma, v2 plus w2, comma, v3 plus w3. Okay? That's basically what we're looking at. Then when we dot u with that value, we end up with u1 times v1 plus w1, comma, u2 times v2 plus w2, comma, u3 times v3 plus w3. Right? That's us taking the dot product. We just dotted u with this value here. Then that's then going to equal, well, we'll just distribute, because now these are just real numbers, we could just distribute. This will end up equaling u1 v1 plus u1 w1, comma, u2 v2 plus u2 w2, comma, u3 v3 plus u3 w3, or w3, yes. And there's your resulting vector. Now what we can do is we can just actually separate these out, knowing what we know about vector addition. So this is now going to end up being u1 v1, comma, u2 v2, right? We'll just take the first values, comma, u3 v3, plus u1 w1, comma, u2 w2, comma, u3 w3. And now when you look at this, this is u dotted with v, and this is u dotted with w. You might have to sit down and think about it or actually read through it to see what I'm talking about. So this is u dot v plus u dot w. And we've distributed. And that's the distributed property. That allows us to do like kind of quite a lot of things when we're working with the dot product. Our next property is that the scalar multiplication by the dot product is going to be associative. So what does that mean? So that means this. If I've got the scalar c, and I'm going to multiply it by u dot v, okay? I take the dot product, I take the dot product first and I multiply by c. This is either going to equal c times u, so scalar multiplication by u, and then dotted with v, so we scalar multiply first and then dot, or it could also be u dotted with cv, okay? Go either way. All right, and so consequently, some of this can actually be kind of handy for us if we're doing kind of multiplication. So if we wanted to multiply c times v first and then dot with u, we can do that, or we can actually kind of factor out, which would be getting back to c times u dot v. So let's do the proof on this. We're going to take c, and we'll multiply it times u dot v. I'm only going to do one of them. I'm only going to do this one here. The second one is exactly the same. So that's going to be c times u1 v1 plus u2 v2 plus u3 v3. And that then equals, when I multiply by c, it's going to be c u1 v1, because I'm just going to distribute it in the v. c u2 v2 plus c u3 v3, which is great. And if you notice, right, basically we'll just treat this as components as individual components. And so what is that? Right? That is just simply CU dotted with V. There's no other real way to like kind of show that that's the case. Just go down there and think about it for a second, that's exactly what's happening, right? That we've got CU first, and then we'll dot it with V. Okay, you can go in and kind of check that as well. Our last property is going to come in super handy, and it's this idea that the magnitude of the vector is the dot product with itself, or the magnitude of the vector squared is the dot product with itself. So let's take a look at that. This is actually going to be one of these identities that we're going to utilize quite a lot. It's going to become really very handy. And so this ends up equaling V dot V. Okay, that's what we're saying. So if I take the magnitude of V and I square it, what I end up with is the square root of V1 squared plus V2 squared plus V3 squared, right? Okay, that's the magnitude of any vector. You're just going to go through in component form. You'll just take the first component squared plus the second component squared plus the third component squared, then take its square root. Then we're going to square that. So what do we end up with? We're going to end up with V1 squared plus V2 squared plus V3 squared. And then what is that? That equals V1 times V1. And now we're actually, let's, instead of taking the dot, we'll use a V1 V1 plus V2 V2 plus V3 V3. Well, what is that? That's the dot product squared. I mean, that's the dot product, right? That's just the dot product V dotted with itself. V dot V. Okay, see that? Because the first component of V is V1. Second, same thing. Second component of V is V2. Third component of V is V3. So there we are. Super handy. It's going to come in really handy for us. We'll use it quite a lot inside of this class. So now what we're going to do is we're going to utilize, we're going to start talking about the dot product and using it to do one of the most handy things that we can do with it, which is finding the angles between two vectors, right? Which is going to be, because it kind of expand and expand and expand, we're going to use it a lot, okay, as we utilize the dot product. So let's imagine that we've got U, right, some vector, and we've got V. And these are two vectors, and we're going to write these in 2 dimensions. And let's say I've got U here, okay? There's U. And then I've got V here, okay? And in between these two, there's a vector theta, okay? Now, if V happens to be one of our coordinate axes, this actually isn't so hard. We do actually know how to work with that if V happens to be a coordinate axis. But what if it's not? Okay, what if it's not? What can we do with that, right? Okay, or what if U is not a coordinate axis? And so consequently, that's where this kind of comes in handy. And then again, we're going to utilize this a lot as we do more and more work with proof. So we're going to start out, we've got a theorem, all right? And we're going to prove this, prove the theorem, okay? And that the theorem is this, it's basically an equation. It's that U dotted with V is equal to the magnitude of U times the magnitude of V cosine theta. And this is going to be huge. This is a huge equation as we work with the dot product. Something you definitely want to, kind of memorize. Know this. And then we'll expand it too. You'll need it in other places as well. So let's take a look at why that's the case. Let's look at a proof. So what I'm going to do is I'm going to set up, I'm going to have U. There's my vector U, and then here's my vector V. Okay? And what I'm going to do is I'm going to draw this line here. There's another vector, okay? And this vector is actually V minus U, right? And there's my third vector. Now what I have is I have a triangle. I have a triangle where the 3 sides are U, V, and V minus U. What I'm going to do first is I'm going to utilize my law of cosines, okay? So the law of cosines. And if you remember, the law of cosines essentially said if I have 3 sides, A, B, and C, by the way, and here's theta, okay? So A squared plus B squared minus 2AB cosine theta is going to equal C squared. And that's essentially the relationship that we have here. If we look, we can actually go in here and we can replace A and B. These are lengths, okay? These are lengths of sides, as is C squared. That's also a length, all right? And so what we get here, using the law of cosines, if I use that, I'm going to let A right, equal, A will end up being the magnitude of u. We'll let B equal the magnitude of V. And we'll let C equal the magnitude of V minus u. All right, now what we're doing is we're just replacing our sides, and then theta remains theta, because it's the exact same thing. So now all I've got to do is I've got to plug these things in. So I've got u squared plus v squared minus 2u v cosine theta, and that theta is that angle that we're looking for, and that's going to equal v minus u squared. And there we are. So what I'm going to do now is I'm going to focus in on this v minus u squared. Okay? I'll usually leave the other side on its own for just a moment, but v minus u squared is going to end up being v minus u dotted with itself. Remember that? That's one of those identities that we actually figured out. Right? That if we dot a vector with itself, we're going to end up with, okay, its magnitude squared. Right? Its magnitude squared. And then we can actually use that distributive property, and we end up with v, or v minus u dotted with v minus v minus u dotted with u. Okay? So basically that's our distributive property, and also actually what we did is we also factored in a scalar. Now, what we can do then again is we can multiply again, or distribute again, and we end up with v dot v minus u dot v minus v dot u plus u dot u. Right? Because you got a negative negative, just to kind of like make sure that everybody catches that that's where that negative is going to come in. And then if we substitute again, what we'll end up with is this is the magnitude of v squared minus u dot v, and then we'll make this minus, and remember we can commute, so this will be u dot v, and this by the way was plus, not a dotted, plus the magnitude of u squared, which is the magnitude of v squared minus 2u dot v, because there's two of them, plus the magnitude of u squared. So take a second, pause for a minute, like sit down and go, okay, that's where, take a look at like those identities as you were working, and see where that kind of comes in, where the identities come in, and where they play a role inside of this part of the proof. So now I'm going to come in and I'm going to compare that, okay? I'm going to compare that to this right here, right? I've got u squared plus v squared minus 2 times the magnitude of u, the magnitude of v, cosine theta, right? Using that law of cosines, and it's going to then equal this right-hand side over here, okay? And now all I've got to do is I've just got to go in and I've got to use some algebra, because all of these, because they're dot products and magnitudes, they're just numbers. So I'm going to subtract out, I'm going to subtract minus v squared and minus u squared from both sides. So minus u, the magnitude of u squared, and minus the magnitude of v squared. And that leaves me with negative 2 times the magnitude of u times the magnitude of v cosine theta equals, and that'll be negative 2u dotted with v. Next up, we're going to divide out the negative 2's. And what we're left with is the magnitude of u, magnitude of v, cosine theta equals u dotted with v. And those two things are now equivalent. They're the same. Okay? And that is in fact exactly what we wanted to prove. See that? That's what we wanted to prove. That if we dot a vector with another vector, it's going to equal the magnitude of the first vector times the magnitude of the second vector times cosine theta. All right, kind of cool. You might want to watch this, see how it kind of gets done. It's not too terrible. It's just utilizing that dot product and learning more about the dot product. Now, so what's the angle between U and V? Right? Well, it's sitting right there. All we got to do is we got to do just really a little bit of algebra and some dot producting. So we'll take this. We've got U times V magnitude cosine theta equals U dotted with V. So that gives me that cosine theta is going to equal U dot V divided by the magnitude of U, magnitude of V, okay? And so theta then is going to equal, all right, the cosine inverse of U dotted with V divided by the magnitude of U times the magnitude of V. Okay? And this is for theta, okay, greater than or equal to 0 and less than or equal to pi. So between 0 and pi, okay? And we'll basically, I mean, like whatever else you've got there, you know, you take a look at your two vectors, and that's just a frame of reference as to whether or not you're like, oh, is it 0 to pi? Is it 3 pi to 4 pi? It doesn't really matter. Just keep those values between 0 and pi. We're going to have that be the range of our equation here. Okay, so that's how we find it. There it is. Let's take a look at some problems and do some problems with that. Okay, so let's take a look, and we're going to start out. We're going to find the angle between I plus j plus k and 2i minus j minus 3k. So what we'll do is we'll say, okay, well, I know that that value is going to be cosine inverse, okay, of, and it'll be, in this case, it'll be 1, comma 1, comma 1, dotted with 2, comma negative 1, comma negative 3. So in component form, those are my two vectors. And then the magnitude of 1, 1, 1 times the magnitude of 2, negative 1, negative 3. So now what I want to do, I actually kind of want to go figure out what these things are first. So I'm going to find the magnitude of 1, 1, 1 is going to equal the square root of 1 squared plus 1 squared plus 1 squared, which equals the square root of 3. The magnitude of 2, negative 1, negative 3 is equal to the square root of 2 squared plus negative 1 squared plus negative 3 squared, which ends up equaling the square root of 14. And then we'll take the dot product. We'll find that dot product, 1, 1, 1, dotted with 2, negative 1, negative 3, will end up equaling 2 plus negative 1 plus negative 3, which ends up equaling negative 2. So this angle, theta will end up equaling cosine inverse of negative 2 times divided by the square root of 3 times root 14, which equals cosine inverse of negative 2 over the square root of 42. Plug that into our calculator, okay, and we'll get a number of radians. And what that ends up being is 1.8845 radians. There we go. Okay. What about, let's find theta, right? The angle between the two vectors. And that'll be for 2, 5, 6. And negative 2, negative 4, 4. Okay, so we're looking for theta. All right. And so what we're going to do, we're going to do the same exact process. Let's actually just do it step by step. We'll find our dot product. Find u dot v, let's call it, which equals 2, 5, 6, dotted with negative 2, negative 4, 4. And that equals negative 4 minus 20 plus 24, which ends up equaling 0. So there's the dot product. Then we'll have our magnitude of u. magnitude of u is going to equal the square root of, and this will be 2 squared plus 5 squared plus 6 squared. Okay? And so that ends up being, right, 34 plus 36. Excuse me, 29 plus 36. And so that's the square root of 65. And then we have the magnitude of v, which equals the square root of negative 2 squared plus negative 4 squared plus 4 squared, which ends up equaling the square root of 36. So what we get now is we get that theta is going to equal cosine inverse of 0 over the square root of 65 times the square root of 36. Okay? And so that means that theta equals cosine inverse of 0. And so what's cosine inverse of 0? Well, that means that this is, in fact, pi over 2. If we plug cosine of pi over 2, that's what ends up equaling 0. So the inverse of 0 is going to end up being pi over 2. Okay? And that's actually going to establish for us something actually really important, which is that if we have two vectors and their dot products end up equaling 0, what we're going to get is that the angle between the two of them is going to end up equaling pi over 2. So this work with vectors leads us to an actual crucial result, a really, really important result. And that is that two non-zero vectors, u and v, are orthogonal if and only if u dot v equals 0. So the first thing I want to point out here, you might be saying to yourself, what do you mean orthogonal? And what I mean by orthogonal is that it forms a 90-degree angle. We use the phrase orthogonal rather than perpendicular because perpendicular really only works out in 2 dimensions. Orthogonal, we can talk about vectors being orthogonal in n-dimensional space. And actually, if you think about it, you can have vectors that are, there are an infinite number of vectors that are in fact orthogonal with another vector in 3D space or in 4D space, right? Because the way that we might think about orthogonal kind of depends upon, you know, what dimension we're looking at, all right? And so consequently, like, there's a lot of different ways to think about orthogonal. There's a lot of different ways that we can view what it means to be orthogonal to form that 90-degree angle. And so that's why we utilize this different word, the different word orthogonal, okay, to define what it means to be perpendicular in what we say n dimensions, as many dimensions as we want, okay? So let's go out and let's in fact prove this. We're going to prove this. And what I want you to notice is that we've got this if and only if statement. So what the if and only if statement means is that if I know that the two vectors are orthogonal, right? That is that the angle that they form is a 90-degree angle, then I automatically know that their dot product is 0. That's the first thing, okay? Or if it is the case that I know that u dotted with v equals 0, then I automatically know that the two vectors are in fact orthogonal. All right, so what that means is that we can basically go either way. The two are what we call equivalent statements. So we'll start out with this one. We're going to say that let u and v be orthogonal. And we'll let theta be the angle between them. Since they are orthogonal, that means that theta equals pi over 2. It's a 90-degree angle. So theta equals pi over 2. Okay? Thus, right, remember we have this equation. We've got the magnitude of u times the magnitude of v times cosine theta, or cosine in this case pi over 2, because that's what theta is equal to u dotted with v. Now we know that cosine pi over 2 equals 0, so consequently what we get is that u dot v equals 0. So thus, u dot v equals 0, and we're done with that part. With just that part, if we start out with the two non-zero vectors are orthogonal. Okay? Now, by the way, that non-zero part, we should probably get into this, that actually just tells me that the magnitude of u and the magnitude of v are not actually 0. Okay? It's going to play a role inside of the second part of this proof, but for this one, it doesn't really make that much of a difference. Let's go the other way, okay? We call this the front way. Let's look at the back way. And so in this case, we're going to start out with let u dot v equal 0. So we've got the two of those equaling 0 when we dot them. And so, by definition, right, what we get is we get the magnitude of u times the magnitude of v. Cosine theta is going to equal u dot v, right, which just equals 0. We said that already. Now, since u and v, u doesn't equal the 0 vector, and v doesn't equal the 0 vector, that is, they're non-zero vectors, the magnitude of u is not equal to 0, and the magnitude of v does not equal 0 either. That's actually going to be kind of helpful because that's going to prevent us from having to divide by 0. All right? Now, by the way, that's not equal to 0. Couple things, if you want to think about it this way, the only vector that has a length of 0 is the 0 vector. That's going to be the only one. Every other one has a non-zero length, right? Like, because you start at the origin, you go out to whatever that value is component-wise, that gives you a little length. So only the vector that starts at the origin and ends at the origin, okay, is going to have a length of 0. And so hence why we end up with this whole idea of the 0 length. So now I've got all of this. So I get now, I've got, so u, magnitude, v magnitude, cosine theta equals 0. I can divide through by the magnitude of u and the magnitude of v, because they're not 0, so consequently I can divide by them. Thus, cosine theta is equal to 0. And since we are actually only looking at the values of theta between 0 and pi, okay, that means that theta, so theta equals pi over 2. Thus, u and v are orthogonal. And that's how we actually go about proving this. All right? And that proved our statement. We proved on the one hand, if I start out knowing that u or v is orthogonal, then u dot v equals 0. Or if I know that u dot v equals 0, then I know that u and v are in fact orthogonal. I know it both ways. It's actually kind of handy. It's going to be an important little piece of information that we're going to be using. So let's look at an example. Let's ask ourselves, are p 105 and q 10, 3, negative 2, are they orthogonal? So the way that I'm going to do this to determine if they're orthogonal is I'm going to figure out, is their dot product equal to 0? That's what I'm asking here. Is p dot q equal to 0? If it is, the two are orthogonal. That's the proof that we just had there. So we got 105 dotted with 10, 3, negative 2. And that's going to end up equaling 10 plus 0 plus negative 10, which equals 0. So P and Q are orthogonal. We just found that their dot product was equal to 0, and so that proves, in fact, that the two vectors are orthogonal. Okay? Great. Perfect. Let's try another one where we're, kind of just utilizing this piece of information. So let's ask ourselves for which value of x is, and we'll have P equal to 2, 8, negative 1, orthogonal to Q equal to x negative 1, 2. So we want P dot Q to equal 0. So P dot Q is going to be 2x minus 8 minus 2. Right? Multiply 2 times x plus 8 times negative 1 plus negative 1 times 2. And that's going to equal 0. So we've got 2x minus 10 equals 0. 2x equals 10. So x equals 5. And that's our answer. Right? Just a little algebra trick, something that we might be able to use. Okay? But, nothing too terrible. Something that might be kind of valuable for some other things that we do later on inside of the class. So, what we've done now is we've actually talked about the dot product quite extensively. So we have just begun with the dot product. And we're going to be utilizing the dot product quite a lot. We've looked at how do we calculate the dot product. We've also talked about some of the properties of the dot product, and we're going to be utilizing those a lot. So even though you don't need to memorize them, you should actually feel comfortable with them and see them like when I actually use them. I'll bring it up, but you want to kind of sit there and go, oh, okay, I know what he's talking about with those properties. you want to make sure that you do memorize that one where the magnitude squared equals a vector dotted with itself, because that's going to be super important. And in addition to that, we also talked about the relationship between the dot product and the angle between two vectors, and that's going to be crucial. Finally, key point, key piece of information, because when you get into math, you're going to see how important this actually really is, okay, is that if we dot a vector with itself, okay, and that dot product equals 0, that means the two vectors are orthogonal. Or if the two vectors are orthogonal, that means that their dot product equals 0. That's going to be actually quite crucial for stuff that we're going to be doing later too. All right, so this concludes this particular lecture. In the next one, we're going to be talking about projections, okay, and the value of projections as well.